It's my great pleasure to introduce our next speaker, who is our indispensable organizer, and who is, let me say, the heart and the soul of our conference during all 11 times, Professor Karapetyants.
Thank you very much for a very nice introduction. It's my pleasure to give a talk here. And, well, the title of the talk is here, so I just changed a little. Sorry. I did change a little title in the program, and the program is kind of different, but you see here is Hausdorff-Berezin and Hausdorff-Zoo operators. So these are two classes of operators I will be speaking about. And you can see 5 papers. I will base my talk on 5 papers, but not all of them. Yeah, I will step in details. Mostly I will be speaking about the first paper by Karapetyants, Samko, and Kehedzu, and by the recent paper Karapetyants and Merotin. And you see the papers 3 and 4 are kind of general theories, so I will refer to this general theory just to show that this particular cases inherit in some sense known tools from general theory of Hausdorff operators and homogeneous operators, or operators with homogeneous kernels. And paper, also recent paper 5 with Grudsky, Karapetyants, Merotin, just submitted. Well, I will not speak about this paper, just mention what we were doing in this paper on some slides, but basically I will skip this paper. So just to show you what I have in mind when I speak about Hausdorff-Berezin and Hausdorff-Zoo operator. So let me just write some formulas. Operator K applied to function f at the point z equals to integral of the union disk. Here we have kernel K, W, F Möbius transform phi z W, dAW, or basically instead of dA I will use dHW, where dHW is a Haar measure, Möbius invariant Haar measure, equals to dAW. dA is just plain Lebesgue measure, 1 minus W squared. So, but this would be our Hausdorff-Berezin operator. And Hausdorff-Zoo operator, you take function, and of course Möbius transform, I just write down it, phi z of W equals to z minus W, 1 minus z bar W, automorphism of the unit disk. Okay, so Hausdorff-Zoo operator, we call it in such form with Merotin, Kf of z equals to integral over unit disk. Also, well, we use here actually, instead of k, we use for kernel phi, but doesn't matter, of course, phi of w, f, and here instead of phi zw, you have phi wz, which is quite natural if you have kind of this shift, so I would not consider the other shift, daw. So at some point these operators are counterpart to each other, but they differ from each other drastically, and I will speak about it. So also let me mention, because there are words Hausdorff, Berezin, etc., and homogeneous operators. So basically there are many papers devoted to so-called Hausdorff operators. And also many papers devoted to operators with homogeneous kernels. In the one-dimensional case, this would be the same, and whole theory goes back to the Hardy-Polya theory, very well known, but in multidimensional case, these classes are different. But in any case, these are big classes, and operators from these classes possess some particular features and some tools used in study of operators from these classes. And as I said before, even though we consider these particular cases, and even though these cases are kind of new operators, which are, you see, this theory kind of real analysis theory, but this kind of new operators in complex analysis, but still these operators, study these operators, almost sometime, not sometime, almost in all cases can be justified or by the theory of the operators, or tools from theory of the operators can be applied. Okay, so you see, actually, this paper was the first paper was first in this direction, and it was an idea how to translate operators of the homogeneous kernels to complex case. And well, with Karapetyants in 2018, we just took classical operator of the homogeneous kernel on R2, and by some translation, by modifications, change of variables, we reduced it to the unit disk. And we obtained something ugly, which is not useful. So we realized that it's not like direct generalization. You should not just take a direct generalization. You can use idea of homogeneity, but not just trying to generalize directly. So that's what I'm saying. These operators take the idea of homogeneity. They are not direct generalization of what we know in real analysis. And one more remark, just to this idea of homogeneity. If you take this operator with R measure, then you have very nice property KW FZW dH of W equals to integral of d K phi ZW F of W dHW. So this nice invariance property, kind of convolution, right, type property. Of course, you can write something similar to for these operators with Lebesgue measure, but then you will have a Jacobian. You can impose some conditions on Jacobian, but of course you can do this, but it will not be so nice formula. So maybe this nice formula was the reason why we really started to work with these operators in this first paper with Haar measure. But still, I am sure that it's worth to consider with this measure, even with general type of measure. Okay. So, well, I've been speaking about Hausdorff operators. Finally, I can show you the most general definition. Hausdorff operators usually associated with matrix A. Here you can read everything. I will not waste your time reading these letters. So this would be the most general form in our understanding of Hausdorff operators. Sometimes people call operator of the time 1.2 Hausdorff operator, but this is not true. This is exactly operator of the homogeneous kernel. And maybe because of this reason, in the paper with Liefland, in third paper with Liefland, we tried to put conditions such that these conditions will somehow describe Hausdorff operators. You can read these conditions. All these conditions are supported by examples in our papers, but this paper is not like ideal paper. We not always have the criteria. Sometimes we have just suggestion or support by examples. Not always we have just criteria. But anyway, we are most sure that Hausdorff operators, such operators that should satisfy these 5 properties. And as I said in this paper with Liefland, all these 5 properties justified either by mathematics or justified by showing examples. Sometimes you cannot prove this in a general scheme, but you can reduce your operator to a simpler case, and in that case you can prove this. So that's what I call example, for instance. Okay, now, as I said, this basically is not Hausdorff operator 1.2, but operator with homogeneous kernel. And general definition for operator with homogeneous kernel is here. So, homogeneous of minus n power. So, it should satisfy the 2.1, the homogeneity property with power minus n, and should satisfy the rotation property. So in this case, people call operators with homogeneous kernels. In our paper with Karapetyants, we go further and we consider not only integral operator but just homogeneous operators, because we realized that this property should not be connected with the kernel but rather with measure on measure space. But this is another story. Okay, and as I said, in one-dimensional case, homogeneous operators and operators with homogeneous Hausdorff operators coincide. And as I said, I repeat because it's very important that all this goes back to this very nice, very famous hard-deletable polar theory. So we consider really good operators that contain good examples inside. Okay, now we go to our first type of my presentation. First subject of my presentation of our results on Hausdorff-Brezen operators, and I need to explain why Brezen operator, why Hausdorff-Brezen. Hausdorff you already understand because of this nice kind of homogeneity property or invariance property. Why Brezen? Because first and the most important example in this class is the very famous Brezen operator, Brezen transform, known in the complex analysis, plays the same role as Poisson kernel plays real analysis. So Brezen transform is an example of Hausdorff-Brezen operator. That's why the word Brezen comes to our definition, because it's just generalization of Brezen transform. Basically, you have this integral, so you think, why don't put here a kernel? Okay, so you don't have kernel, so why don't put here a kernel? You have the generalization. That's what we have here, exactly. Okay, so that's how Brezen comes to this definition. And here again I rewrite this, what I wrote on the whiteboard. Here is Har measure, here is the nice property of invariance, etc. And as I said, motivated by the above discussion, we call these operators Hausdorff-Brezen operators. Okay, so more examples. Yes, we still have more examples. This averaging operator also belongs to the class of Hausdorff-Brezen operators. The averaging operator with respect to this disk, pseudo-hyperbolic disk, was used by, for instance, Matelievich and Pavlovich to prove Yudovich-Zakharyuta Forelli-Rudin theorem about boundedness of the Berman projection for this parameter P. We know that Berman projection is not bounded from LP to AP for this P. But when you consider holomorphic functions, you don't need to consider LP space. You may consider the other Banach space or Normed space from which you have at least one bounded projection. And if you have at least one bounded projection, then you can operate with this holomorphic space. You can prove duality. You can prove whatever you want, not whatever, of course, but you can prove many things. So using these averages, they constructed kind of generalization of LP spaces in such a way that function belongs to LP, their LP space, if this average belongs to regular LP. And they managed to prove boundedness of Berman projection in this new setting. And you see I write here Yudovich-Zakharyuta, Forelli-Rudin. Actually, Yudovich-Zakharyuta proved this result in, I guess, in 1963 or even early, but nobody knew about these results because it was never translated. And people always refer to Forelli-Rudin, which is kind of 1970, 10 or more years later. Okay. Well, I will skip these formulas. I just point attention to this coherent state. This is normalized Berman kernel. We will use this formula 4.6 for our further purposes. So this would be Berman kernel, and this is its normalization. So please remember this formula. I will just refer to this formula as 4.6. Well, when you deal with integral operators, usually you take operator of two variables, because you have inside here just one variable, but you can replace here, you can replace to have here these two variables, but they are connected. But instead you can write, you can of course place equation. What if I would write k0 of ZW. So in which case I will get our Hausdorff-Berezin operator. And the exact answer is here. So in case of this symmetry, you will have exactly the Hausdorff-Berezin operator. It means that there is a kernel, one variable kernel, that can be represented in this way. Okay? If you go further and ask for more stronger conditions, symmetry with respect to all Möbius transforms, where A is arbitrary, A runs over the unit disk, then in this case, exactly in this case, you have Hausdorff-Berezin operator with radial kernel. So you can read the proposition here, this condition, so if and only if, right? So this would be the condition for radial kernel. So for this form of Hausdorff-Berezin operator for radial kernel. Radial kernel quite nice because at least you recover Berezin transform by radial kernel at least. And in this real case, you can prove this algebraic properties that makes me think that you can advance in algebraic theory, but I'm not algebraic guy, so I'll just keep this slide. Well, you remember I said that these operators inherit in some sense properties of operators, Hausdorff operators, operators as homogeneous kernels. In this particular case, this means that we can apply the method, of course with modifications, method of proving boundedness to proving boundedness in our particular case. So setting this K as above, or in case of radial kernel, you just can simplify. We can just prove the boundaries in L1, and the norm is bounded by K. More general theorem, boundedness in LP, we introduce K1 and K2. You can see kind of non-symmetry here, but it's natural for the situation. And here you can see this coherent states, normalized Berman kernels. So the theorem says if there exists at least one sigma such that these numbers are finite, then the operator is bounded in LP and norm is bounded by this constant. Of course, when you prove boundedness, you also think about necessity. But similarly, as in the case of operators of general kernels, you cannot prove, at least we cannot prove at least necessity for a general situation, but we can prove also, as in case of homogeneous kernels, we can prove necessity in case of positive, non-negative kernels. Well, I don't waste here space. I don't write kappa 1, kappa 2, but you see kappa 1, kappa 2 the same as K1, K2, but with supremum replaced by infimum. Okay? So these are kappa 1, kappa 2 with infimums. So on the condition of non-negativity of the kernel, the following theorem 4.7 gives you necessity condition. And in particular, but important case of radial kernel, and I repeat that Berezin transform you get from radial kernel and many other operators also. So in this case of radial kernel, we have if and only if conditions. So here you can see the theorem 4.8. Okay. Also, I mentioned that these operators must possess some property of averaging. The idea here is trivial. I mean, if you formally put epsilon 0, then phi z of 0 equals to z, and you can put outside f of z, so like this. That's formally, but the exact theorem stays if kernel belongs to L1 and the value of integral equals to 1, then you have the following formula of approximation. So Hausdorff-Berezin operators give you very nice tool for approximation. Now, Hausdorff-Zoo operator. You see, Hausdorff-Zoo operator is something similar. You just replace Z and W, vice versa. But this situation changes the operator drastically, and actually it was Mirotin who started to study these operators. But before, without this kernel, phi, like you don't have this kernel, phi capital, this operator appeared as Berezin operator also as a counterpart to Bayesian operator, appeared in the paper by Keihe. And I had a conversation with Keihe, and he said that, well, it's small operator, it's just two-dimensional operator, not maybe not so interested for study. Yes, it is indeed two-dimensional operator, and it will be two-dimensional even if you will have a kernel, and this kernel would be holomorphic. But if this kernel would be general, so the operator changes drastically. And so it makes much sense to study this kind of operators. I repeat that the operator of this type appeared in papers. I don't think, maybe it's not the first paper, 2020, maybe it was before. Okay, okay, okay. So again, as in case of Hausdorff, and why Hausdorff zoo? Now you understand, because Hausdorff means that we consider operators that possess some kind of homogeneity property. Zoo because first operator he considered. I mean, I learned from him, from Keihe zoo, about this operator. So that's why we call these operators Hausdorff zoo operators. So also, as in case of, in previous case, we can apply with some changes technique of boundedness, of study boundedness of homogeneous operators to prove this sufficient condition, and this also on the assumption that kernel is positive, also negative, also necessity condition. Okay. Now that's what I wanted to mention. Even in the case when you have holomorphic part and radial part, you see it's called Hausdorff operators with factorized kernels. Means that your kernel is split into two functions. One is holomorphic, another is not holomorphic. So in this theorem, we take radial function times monomial. In this case, operator is very nice. It's almost diagonal. It shifts. You see, n of z equals to z to the power n. So n, where it is? I don't see. Here. n m plus n just shifted by, multiplied by z to the power n, and multiplied by a constant, by weight. So it's almost diagonal, but with kind of shift. This makes us this makes useful to give some immediate properties, and also we can calculate these numbers, singular numbers, using the Jacobi polynomials. And as I said in our paper with Grutsky and Mirotin, we managed to apply stationary method files to prove not only this kind of behavior, but also prescribed kind of behavior. Like if you impose some condition on kernel, we have some exact estimate for the singular numbers. But I will not speak about this paper today. And as I said, this operator is almost diagonal, but still there is a tool how to work with almost diagonal operator, and this theorem allows us to do this. So based on this theorem, we can give, even for a general situation, X here is a general Gilbert space of holomorphic functions. It can be Dirichlet space, Berman or Hardy space, and many others, such that the basis n is orthogonal basis in this space. So this would be the sufficient and necessity condition for compactness. And in more general situation, when you have this type of kernel, we have only sufficient condition. Also, if you have nice such representations, then you can get some nice theorems, like speak about nuclearity, and prove some formulas from traces. Let me not read this theorem. Here it's written clearly, conditions and statements. So the idea is that this operator is kind of complicated, but it allows to go deep into detail, go deep into the study of this operator. Well, let's come back to just holomorphic kernels. As I said, this operator is two-dimensional. Maybe it's better just to go to the next slide. So even if you have this general kernel from Berman space, your operator acts on function f like this. So it preserves only zero coefficient from the function f and preserves this first coefficient from function f. And that's it. So this really small operator for galomorphic kernel, instead of the previous case when it was almost diagonal case. Okay. So having this nice information, we can prove spectral properties, etc., etc. And if you go to radial kernel, only radial kernel without an addition, then your operator is diagonal, and because of it is diagonal, you can apply many known results to speak about compactness, to speak about Schatten ideals, to speak about many other properties based on the decomposition for singular numbers. And also you can apply multipliers theory to prove sufficient condition for boundedness. And I will come back once again to this paper by Grudsky, Karapetyants, and Mirotin. Like here you can see that we impose if lambda n equals to z, then h phi extends from etc., right? But in our paper, we impose condition on kernel such that we have the prescribed behavior. So we go further and deeper, and we state conditions on kernel such that ensure that conditions ensure boundedness in Z or another space. And well, I didn't check my time, but I guess it's
8 minutes.
well. Anyway, I don't have more slides. Sorry.
Ладно, ставить.